Hey y'all! Today we are going to talk about solving log equations with exponents and log properties. So before we get started, let's talk about what we learned last class. Last time we were together, we learned that when we see x in an exponent, we always undo an exponent with a log. The inverse operation is a log. So just like multiplying and dividing go together, adding and subtracting go together, exponents and logs go together. So today, when we see x inside a log, we're going to use its inverse to undo it. The inverse operation is going to be exponent. And please remember, whatever the base of your log is, that's going to tell you the base of your exponent. So your base is your base. Let's take a look at this first one. We want to solve for x. That's our goal. And right now, x is inside of the operation of log. So how do we make log go away? We know that logs and exponents undo each other. So how do we use an exponent to get this? Well, we're going to use a process called exponentiating. Now, that's a big, scary word, but it means we're going to take the left side and make it into an exponent. We're going to take the right side and make it to an exponent. What must every exponent have? A base. Whatever the base of your log is, in this case it's 3, we're going to make the left side into an exponent by giving it a big old base of 3. Same thing on the right side, we're going to make it into an exponent by giving it a big old base of 3. Now we can solve this problem. Because exponents and logs undo each other, these operations say bye-bye. And we are left with just plain old x on the left side. So we can write this as x equals 3 to the 4th power. Now we can put this into our calculator. So we can put 3 to the 4th power in, and we get that x is equal to 81. So again, every time you see a log, turn both sides of the problem into an exponent. So here we've got another one. We see a log. This time it has a base of 2. We're going to undo a log with an exponent. And in order to do that, we need a base of 2 over here and a base of 2 over here. Exponents and logs undo each other, so we say goodbye. And we are left with x equals 2 to the 1 over 18th power. Then we can put this into our calculator. 2 to the 1 over 18th power. And we are left with 1.04. This next one, we have a little more on the inside, but remember, when you are solving, you have to go with the outermost operation and work your way in. We can't divide by 3 until we make that log go away. So how do we make the log go away? By exponentiating. We're turning both sides into an exponent. So here, these say goodbye, and we are left with 3x equals 5 to the 2.5. Please don't put this in your calculator yet, because it's going to make you round more than once. Wait until you get x alone, and then you can put it in your calculator. So here, we can divide both sides by 3. Let me change the size of this a little bit. So divide by 3, and now we can say x is equal to 5 to the 2/5 or 2.5 power over 3. And we can put this in our calculator. 5 to the 2.5 power, and then that whole thing is over 3. So we end up with 18.63. All right, same deal here. We can't subtract 4 from both sides because this is all inside the log. So we have to get rid of the log first. Now, how do we get rid of a log if we don't know its base? Well, we actually do. We get to assume. You know how when you do square root, you're allowed to assume that there's a little 2 in the index, even though it doesn't say it? Or when you write x, you're allowed to assume that there's a 1 in front, even though it doesn't say it? When you see a log, you're allowed to assume that there's a base of 10, even though it doesn't say it. So here, we are going to have log base 10. The easiest way to remember that is 10 is the default because we live in a base 10 society. Ancient mathematicians based our number system on tens because they have 10 fingers. It all goes back to ancient mathematicians making decisions that make their lives the easiest. So we're going to take both sides and give it a base of 10 and a base of 10. We say goodbye. We say x plus 4 is now alone. And that's equal to 10 to the 7/4 power. Wait until you get x alone to use your calculator. So do -4 on both sides. X is equal to 10 to the 7/4 minus 4. Let's put that in our calculator now. So 10 to the 7/4 minus 4, and that gives us 52.23. Now, how could you feel confident about this answer if I wasn't here to tell you it was right? Well, you can substitute it back into the original, into x right there. It's not going to be perfect because you rounded a little bit, but it's going to be close enough that you can feel really good about it. So let's try it out. Let's do the log. Let's go grab our function and we'll take log, and we don't need a base because we know the default is 10. And then our x that we're plugging in is 52.23 plus 4. And we know we want that to equal 7/4. 7 divided by 4. Look at that. Is it perfect? No, because you rounded that 52.23. But is it close enough that you can feel confident? Yeah. 1.7499 is pretty much 1.75. So you know you did the work correctly. Now, sometimes you're going to have to get the log expression alone before you can use exponents. What that means is if you see an example like this, you can't start by getting rid of the log because it's not the outermost operation. Remember, you're unwrapping a present. You got to take off the bow before you can take off the wrapping paper. So in this case, this 2 is causing a problem. So what we do is we get rid of the 2 and we think about the operation. How is 2 impacting the rest of the problem? With multiplication. So we're going to divide by 2 and divide by 2. And now we can rewrite this problem as log base 7 of x equals 3. Once you've done that, you are free to exponentiate. Remember, that means you get rid of a log by turning the left side into an exponent, turning the right side into an exponent. These say goodbye, and we are left with x equals 7 to the 3rd power. So we can put that into our calculator, and we've got 343. All right, let's scooch on over. We got a few more like this. This next one, we can't undo that log yet because we've got this pesky plus 4. The good news is we can undo it with a -4 and a -4. So we're going to have log base 2 of x equals 4. Now that the log is alone, you are free to exponentiate. So base of 2, say goodbye. X equals 2 to the 4th power. 2 times 2 times 2 times 2 is 16, so we're good to go. Let's keep going. Here, we can't get rid of the log because everything's being divided by 2. How do we undo division by 2? We multiply by 2. So we'll have log base 3 of x plus 5 equals 2. Now, you might be tempted to mess with that plus 5, but don't do that yet. That's inside of the log. Remember, you're unwrapping the present. So we get rid of the log now. Base of 3, say goodbye. X plus 5 equals 9. If you left it as 3 squared, that's fine, but I know it's 9. And then subtract 5 from both sides, x equals 4. This next one, we got a couple steps. What do we do first? Well, when you're doing this problem, I want you to think about if you had a simpler version of this. What if you had 2 times k minus 3 equals 7? You'd get rid of the plus 3 first, and then you would divide both sides by 2. We're going to do the same thing with this problem. Even though there's a lot more going on, we're going to get rid of the minus 3 first with a plus 3, and then we can divide both sides by 2. Okay, so we got rid of that minus 3 with a plus 3. Now we're going to divide both sides by 2. Finally, we've got the log alone, so we can exponentiate. So 7x equals 5 to the 5th power. And then we can divide both sides by 7. So x equals 5 to the 5th power, and all of that is going to be over 7. So let's go over here, 5 to the 5th power, and that whole thing is over 7. We end up with 446.43. Now remember to substitute that into your original. Is it going to be perfect? No, because you rounded. But we expect to get pretty close to 7. So let's do it. We're going to do 2 times log base 5 of 7x. Oh, sorry, we have an x here. It's 446.43 minus 3. Let's see, there's an error. What's wrong? Ah, okay. We got to go to the graphing calculator. That's okay. All right, let's try that again. 2 times log base 5 of 7 times 446.43 minus 3. That is pretty darn close to the 7 that we wanted. So we are happy. All right, we got a few more problems to go. If I can get there. There we go. All right, so there is a special case. If we have log base b of m equals log base b of n, so notice that their bases are the same. That's so critical here. If those bases are the same, if they both have a base of b, sorry, I'm out of control. If they both have a base of b, so base of b here and a base of b over here, then we can set the insides to equal to each other. We can say that m is equal to n. So if the bases match, we can say the insides are equal to each other. Please make sure you check for values that make the inside of the log negative. We want to make sure that we don't want to get any values that make the inside of the log negative. So let's take a look. For this example right here, we want to say, or we want to notice that these bases are the same. That means the insides have to be the same. So we can say 2x minus 3 is equal to 5x minus 6. Okay, that jumping is crazy. Okay, I think I fixed the jumping. So now that we know these are equal to each other, we can use algebra to solve. So we can subtract 2x from both sides. We'll have negative 3 is equal to 3x minus 6. Now we can add 6 to both sides. We can get 3x is equal to 3. So x is equal to 1. What did I do here? I did something funky. I wrote the problem down wrong. Sorry. This is 2x plus 3, meaning this will be a positive 3, meaning this will be 9 equals 3x, so x is equal to 3. There we go. All right, now we're in business. Now we need to check and make sure that this doesn't make any of the insides negative. So if we check this one, 2 times 3 is 6, plus 3 is 9. Let's check this one, 5 times 3 is 15, minus 6 is 9. So we are good to go. Let's try this next one. Again, the bases are the same, so that means the insides can be equal. So we're going to say x squared minus 35 is equal to 5x plus 1. And that means we have a quadratic on our hands. So we're going to start by getting everything equal to 0. X squared minus 5x minus 36 equals 0. And now we can factor it. X minus 9, x plus 4 equals 0. And now we can set these factors equal to 0. So x equals positive 9 and x equals negative 4. So these are our possible answers, but we got to check. Let's start by putting in 9. We'll do 9 squared minus 35. And that's 81 minus 35, which is 46. And then 5 times 9 plus 1, that's 45 plus 1, that's 46. So we know that 9 is an answer that works. Let's try negative 4. Let's do negative 4 squared minus 35. Uh-oh. That's going to give us a negative answer. That's going to give us negative 19. So this is an extraneous answer because if we try and find log of negative 19, it's not going to go well. Take a look. Log base 12 of negative 19, that's undefined. So that is why negative 4 is an extraneous answer because it gives us insides that are undefined. So here are 3 problems for you to try. I want you to pause the video and try them, and then you can unpause the video and see them worked out and check your answers. All right, so for this first one, let's do it. We're going to start by subtracting 8 from both sides. We'll get 5 to the x minus 3 equals 68. Now, how do we undo an exponent? We use a log. So we're going to use log base 5 on the left side. We're going to use log base 5 on the right side. And we are going to have x minus 3 equals log base 5 of 68. And then we're going to get x alone by adding 3. So x equals log base 5 of 68 plus 3. Type that in your graphing calculator. X equals 5.62. All right, for the second one, we need to start by getting rid of that negative 6. And we do that with division. So we're going to divide both sides by negative 6. So log of x minus 3 equals positive 4. How do we undo log? Well, if there's no base, we get to assume 10. So raise 10 to the left, raise 10 to the right. These go away. We're left with x minus 3 equals 10 to the 4th power, which is just 4 zeros. Then we get to add 3 to both sides. So x equals 10,000 plus 3. So x is equal to 10,003. All right, this last one, if the bases are the same, we get to say the insides are equal. And these bases are the same because even though one doesn't have a base, we get to assume that it's 10. So we know that these bases are the same. So we get to say that x squared plus 36 is equal to 100. So x squared plus 36 equals 100. X squared equals 64. X equals plus or minus 8. And now we got to test them. So let's test them both. If we do 8 squared plus 36, does that equal 100? Yes. And if we do negative 8 squared plus 36, does that equal 100? Also, yes. So there's no extraneous answers here.